Hello, good morning and good afternoon, ladies and gentlemen. Thank you for joining today's webinar on electromagnetic interference, EMI, with pyroelectric sensors. My name is Oliver Neutert. I'm Marketing Manager EMEA and Asia Pacific at Excelitas Technologies and have the pleasure to be your host today. Before we jump into the presentation, some notes for you briefly on the logistics. In case of questions, please use the questions chat feature on the webinar software located in the lower part of the dashboard. You can undock the question chat window to enlarge this window. We will collect your questions and do our very best to answer all of them after the presentation, time permitting. After the webinar, we will send out an email to all participants, which will also include links to the presented technologies. But now I'd like to introduce my colleague, Prometheus Jasinski, who will take us through the topic of pyroelectric sensors. Prometheus is an applications engineer, infrared detection at Excelitas Technologies, and best suited to explain the influence of electromagnetic interference with pyroelectric sensors and how to deal with it. With this, I hand over to Prometheus, and I'm looking forward to the presentation of Prometheus. Thank you.
Hello, good morning, afternoon, good night, whatever time zone you're sitting in. Thank you very much for this nice introduction, Oliver. Today we're talking about electromagnetic interference with pyroelectric sensors. It's let's say, not a nicest topic, but a very important one, as you will see, and maybe you have already seen it in your experiments or your devices. So let's first maybe see why it is important. Typically, a product development cycle looks like this. Somebody has an idea, or some market research gave a result, and you concluded in the product which you would like to release at the end. And the management tells you you have typically something like 6 months to develop this part, so you have to hurry up to get this project running. Your only boundary conditions are typically the product design and appearance, which is the first thing nowadays to have a nice product at the market so the people want to buy it. And you have to define the features of this product. And the main features which are important for pyroelectric sensors are actually not only the pyroelectric sensor itself, but also wireless communication, which is in our days and products very common. So what you do is you start with a feasibility study or a concept phase. And once you have finished this one, you have to divide your project into different subgroups so that many people can work actually on one product. So you separate typically the hardware development and the software development into different branches. And those ones are then further down broken down to modules. Yeah? So we have a module for the pyroelectric sensor, which is the motion detection module. Then you have a module maybe for the wireless communication features, so all the communication features, other modules in the hardware. And although I'm not writing too many details in the software development, actually the products nowadays, in most cases, even take the biggest portion for the software development. And at the very end, you have the module fusion into the final product. You turn it on, and you want to release it to the market. You are at the very end of the beginning of your project, and you have to submit the product to certain certification tests and operational tests, which contain also ESD, EMI, application, of course, tests and communication tests beneath or apart from other tests. As you can see here in this graph, I have drawn ESD, EMI, and communication as red ones because I get, as an applications engineer, quite frequently feedbacks from this product development stage, which means you are close to the release. You don't have any time to do anything, but you're seeing issues with our sensors or other sensors. And now the question is how to solve it. Maybe first of all, if you are not there yet, what can you do? Typically, you have the two features, pyroelectric motion detection and the feature wireless communication in such a product. And the issue comes from the late fusion and testing. So this would be, for example, such an error signal which you're getting when you turn your antenna on, which is typically also very close to the sensor. So the first recommendation which I can give you is test your wireless communication features as early as possible together with the pyroelectric sensors. So do not separate too long those modules or which you have seen in your project, but try to make it run as early as possible. So actually, how can we frame this electromagnetic interference? I don't want to talk too much about electromagnetic interference by itself, but there are some certain conditions which should be clarified because not all EMI conditions or all EMI issues are the same. So electromagnetic interference I see mainly in two different fields, namely in the far field, which means in the further proximity to the part to be tested. Let's be it the pyroelectric sensor itself. And this is well regulated because there you have a nice separation between the radiated electromagnetic interference and the conducted electromagnetic interference. However, the situation when you turn on such a device and you have an antenna which is close by to the product is rather a near field, which means you are close by to the antenna. This is the self-induced condition, and this is not regulated. So actually, we need to first to make sure that we are talking about the same thing, because the different topics, the different fields do not work together. If you would like to understand electromagnetic interference, it is not only one coupling mode. The most prominent one, when you have a source and the drain, so the drain is affected by something, by the source, which is doing the electromagnetic interference. It's electromagnetic coupling. So you can think of it like having an antenna which emits electromagnetic waves, and they are coupled in again into your system, into the drain. An example for that one would be long sensor LEDs, because we have in most of our products TO cans with LEDs. But also there are other coupling mechanisms like inductive coupling. This example is when you have two nearby coils on your PCB. You can have also capacitive coupling. An example for this one would be a TO can, which is the metal can, over a ground plane. Depending on the distance between the ground plane and the sensor, you're changing the capacitance of your device and you're affecting the EMI stability of this part. And last but not least, there is a voltage drop along thin, long power lines, which can also lead to interference between a source and drain. You can see this topic is quite complicated when you think in theory about this. So my second recommendation is trial and error typically leads to a faster solution than theoretical consideration in simulations. This I am saying because we had quite some discussions also with customers how to simulate something like that, and there are nice simulation tools around the world to be used, but actually there was never a good match and never good understanding of the models which have been applied and the real data found. Why is it so? Mostly due to the solution of the Maxwell equations which are being used. You have to distinguish here again between the near field and the far field. So if you would look into such a simulation, like you can see here by COMSOL multiphysics, even having a very simple horn antenna, you can see that the field pattern in the far field is very complicated. So the simulation itself will be very difficult to set up in a correct manner. And what the simulation does is it solves Maxwell equations for antennas and provides typically terms in field strength which depend on 1 over the distance to the object or to the antenna, 1 over r squared, and there are also terms 1 over r to the third potential or power, sorry. So this is why in most cases, everything which you find around in the internet which concerns EMI focuses on the far field because it's much easier to understand. And this means that you are simply neglecting those terms, 1 over r squared and 1 over r to the power of 3. And actually you can connect this to the frequency where you're looking at. So let's take typical frequencies at which you're looking and operating, communicating. 1.8 gigahertz, 2.6 gigahertz is a very popular one. 3.5 and 5 gigahertz is also the second band for Wi-Fi. When you look there on electromagnetic wavelength, what is the length of a wave when the field polarization changes? You can see that given millimeters, it starts at 167 and goes down to 60 millimeters. And already here you can see that looking at this wavelength only with 60 millimeters at 5 gigahertz, this is 6 centimeters. You can imagine when having a very compact design with a close-by antenna to your product, it is very unlikely that you can simply deduce anything from the knowledge from the far field into the near field, because you are in a different regime of understanding and experience. As I said, the far field typically starts 2 wavelengths away from the antenna, and this is why also all the regulations require actually a certain distance between the antenna and the object. But in the application, you have an antenna which is close to the sensor. So my third recommendation for this one is never conclude on near field performance from far field measurements and vice versa, which means in detail when you have an ESD test, EMI test, and the communication test. Never think that when you have solved an issue in communication that you don't have an issue in EMI testing. And ESD is also can be a form of EMI interference. So you need to test all of them. Let's have a look on the testing of the compliance, how it is defined. You typically do it in an anechoic chamber where you shield everything away from electromagnetic waves, and moreover, everything which is being emitted from such an antenna is being absorbed by the walls around it. This is quite a costly and lengthy test. And there are actually not only one test, but there is a long list of standards which can be applied. So there are military standards, there is the ISO standard, and what we are mostly referring to are the IEC EN 61046 standard, which is used mostly in Europe. So let's have a closer look on this one. This standard actually tells you that a part can have a certain level of EMI, resistance. So not only that you say that it complies with this IEC standard, but you have also to say to which level it complies. When talking to the customers, most of the products, what we're talking about are level 2 or level 3, which means 3 volts per meter or 10 volts per meter. And 3 volts per meter was up to something like 5 to 10 years ago a typical standard for parts, but it comes more and more up that the requirements are now 10 volts per meter. This is why we're getting more and more customers interested in this EMI topic. Moreover, the test criteria depend on the product purpose and target market. So most probably you will not try to pass the highest level, but the level which needs to be passed to release the product to the market, and you will try to find the best solution for this level. There's one particular detail in this standard which I would like to put your attention on. When you look on this picture, this is an illustration for the modulation which you're typically using in such a test. You have the electromagnetic wave modulated with an FM frequency, with an AM frequency, which means the amplitude is modulated by 80% with a carrier frequency of 1 kilohertz. And this is now required to be passed up to 6 gigahertz. So when using only this test, most of our sensors and most of customers' devices will pass the EMI test criteria, which in turn does not mean that they will pass also real-life tests, because the pyroelectric sensor is a slow responding sensor. So it is less affected by the standard amplitude modulation. If you want really put the sensor to the test, you have to do it differently. So let's have a look. This is not now done in a laboratory, but this is not in a standard laboratory and an anechoic chamber, but this is done in our laboratories, what you will see in the following. And let's have a see what we can conclude from this one. So most of the pictures which you will see in the following will be with a similar setup like this one, but of course in a chamber which is protected from EMI. We're using a signal generator which is feeding an antenna where you can change the polarization by the orientation of the antenna. This again is being coupled into a motion sensor on a PCB. And this PCB is being read out by a data acquisition system on the computer. Here already the disclaimer, any EMI findings, any data, any results which we are showing strongly depend on this setup. Not only because you have a near field and far field coupling, which makes a difference between the standards, but also the motion sensor itself on the PCB itself. The whole system needs to be understood in terms of EMI. So please don't think that we can provide you some guidance to the production of the final guidance for the design, because it really depends on the final design of the whole product. And in order to put our sensors to a real condition test, you need to do it close to the digital communication like it is done nowadays. So you have packages which are sending out not continuously, but the communication is typically done with one package, then there is some silence, another package, silence, another package. And so for illustration, I have drawn this here. And let's have a look how this affects the sensor. This would be the response in this experiment for the pyroelectric sensor with a 50 milliseconds package on and 950 milliseconds off. You can see you have on the left side something like the amplitude. Below there is a data point, which is the time axis. And every time when the EMI is being turned on for 50 milliseconds, the sensor is showing you some pickup. Let's elongate this one. We have now the pyroelectric sensor's response when you turn on the packages for 100 milliseconds and 900 milliseconds, it is off. We can compare it directly to the previous one. This is the same color. And you can see when you elongate the transmission time, you can see here a higher amplitude. So let's play this game a little bit further. This would be the response from a pyroelectric sensor for 500 milliseconds on and 500 milliseconds off. So 50% of the time you're emitting electromagnetic interference, and the other 50% there is no emission. Now you might think this goes on and on. When you make it longer, you will see more response, but actually it is not true, because when you compare this now to 800 milliseconds on and 200 milliseconds off, you can see that the amplitude did not only change the polarization like it looks like, but also the amplitude went down. So let's have a look how this looks like as a function of the amplitude, because we can now measure the maximum amplitude and the minimum amplitude of those graphs and present them as a function of the frequency. I forgot this one, sorry. So this would be the response of a sensor for a continuous electromagnetic interference. So once you have turned it on, the bandpass filter will filter everything out and you have zero response. So turning an antenna permanently on will not give you an issue with the sensor. Only once you turn it on at the very beginning, and then it is completely silent. This is what I wanted to show. If you show it as a function, not of the frequency, sorry, as the function of the width of the signal. So how wide or how long did you turn the electromagnetic wave on? You can see that the maximum amplitude increases and has maximum around 500 milliseconds up to 800 milliseconds. The minimum amplitude had already her maximum at 400 milliseconds. So you can see that the biggest amplitude you're getting for a duty cycle in this experiment of about 50%. So this is why in the following, I will present you data which was exactly under those conditions taken, where you turn the transmission with the antenna 500 milliseconds on, 500 milliseconds off, measure the amplitudes of those ones. The recommendation here, keep the high frequency communication very short, or qualify it with such pulses of 500 millisecond long pulses. So it is possible to have a bad performing sensor in conjunction with a close-by antenna to be operated if you are able to keep your communication protocol such way that the pulses are very short. There's another thing which seems to be natural. Yeah? You are affected by the length of the LEDs. And everybody will tell you when you design a PCB, when you have some wires, so the longer the cables are, the more issues you are having with EMI. Let's put it under test. This picture shows you actually in green a sensor with short LEDs, and in red the sensor with long LEDs as a function of the frequency. Again, I have shown here the maximum amplitude and the minimum amplitude, which is being picked up by the sensor. So you can see for this sensor around 2.3, 2.4 gigahertz, where actually the ISM band for wireless communication is being mostly used, the sensor would pick up very strongly electromagnetic interference. So by reducing the pin length in this experiment, you can reduce it to the green curve, and you might get away from the issue which you're having with a close-by antenna, which is disturbing your sensor. However, when you look up to 6 gigahertz, like for example around 5 gigahertz, the situation is actually not better with a short LED length. So here again, you can see you must not only look on one condition, but you need to put the device under the full test. And if you are, for example, using the communication around 2.4 gigahertz and 5 gigahertz, you should test both frequencies. But generally, you can look at the graph and you will find that it's a good idea to keep LED lengths and PCB traces short. There is another recommendation which you will find in our technical notes. The technical notes contain typically drawings like this one, where you can see on the left side a DigiPyro bottom view and some components which have to be kept close to the sensor. So like, for example, in this setup, you would apply condensators 47 picofarad, capacitors 47 picofarad close to the sensor, because this can filter out everything which is being picked up between the microcontroller and the sensor itself. Of course, when you have long LEDs, those capacitors will have only an effect for the lines between the LEDs on the PCB and the microcontroller, but the LEDs itself to the sensor will act as an antenna. So recommendation number 6, foresee filtering capacitors as close as possible to the component in order, when you see issues, to play with different capacitor settings in order to get rid of those issues. So let's have a look on how this affects, for example, here in this experiment, our sensor. You can see here in red a PYD 1598 exposed to the frequencies as given along the x-axis, and looking again at the amplitudes. And we compare it to a setup where you have 47 picofarad on the serial input and on the direct link input. And you can see if you would have issues with your antenna communicating around 2.4, 2.5 gigahertz, with that countermeasure, you would be able to reduce those issues significantly. But don't be fooled. Again, you need to have a closer look on other frequencies as well. And there you can see, when you compare the red line, where you solve the issue at 2.5 gigahertz. In this experiment, you can see that around 3 gigahertz, for example, the issue is even worse. So one countermeasure can introduce an issue somewhere else. So recommendation number 7, look out. Countermeasures do not always solve issues, but sometimes just propagate them to another area. Of course, if you focus only on one issue and you say, I have a problem with the communication with an antenna close by to my sensor, and I'm communicating only at 2.5 gigahertz, with this solution, you will find a possibility to release a product. However, you need to put this under test for the other conditions as well. So again, once you change something in your system, you should test all the other conditions again. Not only communication like solved here, but also you need to redo the EMI tests and also test the ESD behavior of this component. There is one interesting effect which I would like to put to your attention. The component itself has a different sensitivity to electromagnetic interference depending on the orientation to the antenna. So here we have, for example, a sensor which has an issue when you have it top up looking, horizontal, or don't think too much about what it means and which direction it looks, but look at the degree angles. So what we're doing with this component is we are rotating the sensor along its own z-axis in respect to the antenna and looking on the response of the sensor. And you can see that the purple line where the sensor was very unlucky oriented and gives pickup to around 2.3 gigahertz can have an issue, for example, again with your antenna. It might be a solution if you are able to rotate the sensor. So when you rotated it, for example, here by 135 degrees, you will see that the amplitude or the pickup around 2.3 gigahertz becomes a minimum one. Again, here you need to look at the higher frequencies. So once you have solved your issue by rotating the sensor or relocating the antenna, you need to put it under test also for other conditions like here shown, because what was previously bad, the purple line around 2.3 gigahertz, is not necessarily in other frequencies also a bad guy. So around 5 gigahertz, you can see the purple line is actually smaller than for the other orientations. So the sensor would actually behave better. Sometimes we have customers who put only one sensor under test, send them to an EMI laboratory, everything is fine, and then they start production. And the test looks really like the part is not triggering. And actually, sometime after production, they come back and say, oh, we have for a certain fraction of sensors issues with EMI. Others behave good, and some of them do not behave good, especially with the antenna close by. And this might be related to part-to-part variations, which you can see here as a very messy picture. But let's pick up, for example, the purple line here, which gives a very small amplitude. For example, you had this sensor qualified to be the representative for your device, and you have said you are good to go to produce it. And actually in production, you might be unlucky and have such a part like the red line, which picks up more. And this is not only the sensor, but it's a whole combination of the PCB with the sensor with all the tolerances, which gives you different susceptibility to EMI. So my recommendation number 9 would be foresee a safety margin or check not only one part. And what I mean with foresee a safety margin, this means almost all our digital sensors, and of course also the analog sensors, you should be able to look into the raw data signal. You should be able to see the pickup of the sensor while EMI is happening. So please do not use only no trigger as a test or a pass or fail criterion for your test, but try to see the raw data of your sensor and to see what your safety margin is. How much is is it how much amplitude does it give? And it is of course much easier if you have a digital sensor, because then you can access the sensor's data through the microcontroller without having to connect any lines to your PCB, which again change your EMI behavior of the whole PCB. So this is something else which I did not talk too much about this one, but this is actually a big issue for analog sensors, to see what is happening with the raw data in terms of EMI by probing it with an oscilloscope on the PCB, because all the lines which you're connecting to the PCB are changing the whole behavior of your device. And last but not least, you might be already at the condition where you unfortunately did not know about all those issues, and you turned on your device after you have assembled all the modules, and you see, oh, I'm having an issue with my sensor. And this is actually when you start communicating with us. So can we do something for you? And actually, yes, we can. So I would like to show you here as an example only one important message for you. Don't look only on the sensor name, because here you can see both sensors, the left and the right one, what we called PYD1388. It's a dual sensor, which means has two elements, has a gate resistor inside, and actually, when you look at the EMI resistor and the EMI capacitor on the drain source connection between the ground, then you will notice that depending on which four last digits you have, so here the 7083 or 7697, the internal structure of this component can be different. So for example, for the 7083, you have only one resistor and one capacitor. And this was, let's say, for the last 20 years, a standard component which performed very well. Now we have customers who need to test their devices up to 6 gigahertz, and those devices are not performing good enough anymore, or they use the same motion detection units in another project, which was working fine, but now the orientation proximity to the antenna is different, or even they started introducing an antenna for wireless communication features, and then they come back and say the PYD1388 7083 is not enough for us. They actually will say the 1388 is not good enough for us. Yeah? And I will ask which 4 digits are you using, and most probably propose to test the PYD1388 7697. So look out, here is one part name, but 2 different bow numbers. And actually we have a whole zoo of those ones where all the parts have the same name because they behave optically and response-wise the same to the customer, but internally there might be differences. But enough talking, let's have a look. What does it mean comparing a sensor with 1 RC versus 2 RC filtering stages? And this would be, I find, a very impressive picture, because in green you can see how a PYD1388 7083 is picking up EMI in our test versus a PYD1388 7697. I leave it a second on so you can see it's quite impressive which difference it makes to choose the right component at the end. So here again, the last advice, talk to us. We'll find together a solution. And I'm saying this explicitly because I understand that today you would like to protect your own product development and to expose it as least as possible to the market, and not to provide too much information. But at this topic, it might be good to talk to us and find a solution before you really fiddle around for months not knowing what is happening. We might have a solution for you. So today was a rather short presentation, but I believe there are 10 important messages which I would like to recapitulate here. Test as early as possible. So which means turn on your antenna which you have on your device as early as possible. And if you have the possibility, put your devices and modules also to the EMI laboratory under test. Trial and error is more effective than simulations, and you will notice it when you're talking to us that most probably will come up with proposals which are based also on assumptions and guesses, but definitely we cannot give you an answer for your design because each design is unique and has a unique EMI behavior. EMI issues are measurement specific. So like I said, depending which device you're looking at, which test you are actually performing, the results will be different. So we might have some experience with our parts with some customers, but don't think that we can solve it right away for your part. We need also to look for your part separately and look at the details. If you want to test your device, pulse the high frequency to make the issues visible. If you just want to pass the EMI test according to the standards, then you're good to go. You can do it like some customers which have very price sensitive components to release to the market, and the performance under EMI is not critical. For example, maybe a cheap light switch where it does not matter when accidentally, when somebody has a nearby phone close by to it, it turns on. Yeah. If you want to have a high quality part, you should really ask also the testing facility not to modulate the EMI only with those amplitude modulated frequencies, but also try to pulse them. Advice number 5, keep traces short. Number 6, implement the filtering stages close to the sensor. And this can be very tricky, I understand, because sometimes you have only a one-sided PCB and you have the component on the same side. So keeping it very close to the LEDs is, of course, a very challenging task. If you change something, redo all the tests after design changes. Play around with your sensor, antenna rotation and placement. And please check just more than just one sensor, especially if you're not sure whether it is just good enough, because you cannot look into this one, but you are testing it only for a fail or pass criteria, looking on the interrupts only. And finally, talk to us if you're having an issue or starting a new project and you would like to have some advice. We are there for you. Thank you very much, and I hope I could answer some questions up front. If not, here is now the time. We have a couple of minutes now left for your questions.
Thank you very much, Prometheus. Interesting stuff and a nice overview of what to consider dealing with electromagnetic interference from internal as well as external sources. During the presentation, we received quite a few questions from the audience, which I'm going to present to you now for Prometheus' response. Prometheus, one of the questions I received is that how do digital sensors and analog compare?
Yes, this is a good question. Typically, we are saying that digital sensors are performing significantly better than analog sensors. And this has the reason that analog sensors contain only the FET inside, and this FET is changing the voltage output very small. So you need to apply a high amplification, in most cases a two-stage amplification circuit with a bandpass filter after the sensor. And the amplification is something like a factor of 1,000 or even 2,000 in order to see some significant changes in the signal for the ADC of the microcontroller. So this amplification chain is very sensitive to EMI as well. So digital sensors have already inside the ADC, and you don't have the issue with the external amplification circuit. But it is also possible to have a very good EMI solution or EMI performant sensor solution with the analog sensors. If you have, like I've seen, the right analog solution chosen and you have your PCB design under control. Generally, I have to recommend, despite having higher costs for the sensor itself, for the digital ones, it is in many cases much easier to implement the digital one. So please start with the digital sensor, and once you have time in the project and in many cases you don't have, then consider switching to an analog one, unless you have already an operatable and working solution for the analog sensors.
Thank you, Prometheus. The next question is, what about metallics shielding?
Yes, of course. I did not touch this topic here in this presentation because, of course, you can put everywhere metal around. And this is quite a standard for burglar alarms, for example, especially when you are using the old type of sensors. So the solution there was, because they need already to pass the test criteria of 10 volts per meter, they have applied metal shieldings around the sensor in front of the sensor as well. So just giving a small cutout for the sensor in front of the sensor, but also on the back side of the PCB. And this solution was also applied for other designs where you had long LED links. So you can protect the LEDs by themselves also from this one. But I did not want to talk about this explicitly because most of the new developments tried to be cost effective. And if you see an advantage, which I believe, using an EMI performance sensor from our side over the EMI shielding from the metal, then you should really go for the solution, which makes also the assembly much cheaper.
Okay. There's just one last question from the audience, and this is, can you share EMI test data for sensors?
This would be very nice. Yeah? So I can understand this request that somebody asks, I would like to compare the performance of sensors. Yeah? So let's give me, for example, the performance of your SMD part and give me the performance of the TOCAN part so I can test them and choose them one over the other. And we will refuse to do so because I can show you, if you wish, how different the outcomes can be for the two different sensors, where one sensor performs better than the other sensor in one test condition, but in another test condition, I'm able to find a condition where the other outperforms the one. Yes, there are sensors which generally perform better than other sensors, but this does not typically apply to every design. So please refuse from asking us for providing those graphs as representative decision makers.
Okay, so I see there another questions coming in. One question is the difference in thermopile and caliper sensors with EMI. Can you say something about this?
Yes. So generally, we don't have issues with EMI with thermopile sensors. Not that I've seen it on the field, and we have even solutions where SMD thermopiles have been placed in a distance of only 1 millimeter to a 5G antenna in the case of a phone, in order to protect the tissue of a human from the high electromagnetic waves once he touches the device. So those thermopiles have been used actually to protect the human from the 5G electromagnetic waves. There was, of course, some metal shielding in between, but as compared to pyroelectric sensors, there are two major regions two major differences. On the one hand, the pyroelectric sensor has a very strong electric field in the pyroelectric ceramic inside, which by itself is sensitive to EMI and picks up most of it. On the other hand, thermopiles are generally something like 10 times less sensitive than pyroelectric sensors, which means that even if you would pick up something, it would be 10 times less severe to the part.
Okay, thank you. Next question. What is your recommended material to block EMI for long LED?
Metal. So, yeah. Nothing else to be said. Everything which is conductive and where EMI do not pass. Be cautious with metal designs having slits, cutouts, and things like that, because slits and cutouts themselves act like antennas. Of course, you can argue that the length of the electromagnetic wave at 3 or 5 gigahertz is in the order of several centimeters. So in principle, it should not penetrate a metal case which has slits which have just only a couple of millimeters width. But actually, this is again actually an antenna.
Okay, let's see. How do SMD versus through-hole PIR sensors compare to GSM interference?
Yes, so this would come down to the question whether we can provide comparative plots. Generally, I would say the metal can shields better than the ceramic package. On the other hand, the ceramic package has close to no lead length. Yeah, because you can place it directly on the PCB, and moreover, the quality of the crystals inside together forming with the ADC inside a resonant structure picks up less. So generally, I would say SMD performs in most cases slightly worse than sensors and TO cans, and this would actually also justify still the use of the TO cans beneath or apart from the better thermal performance of TO cans. And if you look around on the market, you will see that close to no pyroelectric sensors are being sold in SMD cases just because of those reasons: thermal performance as well as EMI performance.
Okay, then another question is, does dual element versus quad element have a difference?
Yes, it does. So the smaller the elements, the higher the capacitance becomes. Please do not put too much weight on this sentence, because I'm not sure about whether the capacitance increases or decreases. I need to look it up. But generally, you can say the smaller the elements, and this is the case for quad elements where you have 1 × 1 millimeter or 0.8 by 0.8, as compared to dual element sensors with 2 × 1 millimeters. The 2 × 1 millimeter will behave in EMI better than the 4 element sensors. This is a general takeaway which I've seen in the data.
Okay, one last question is, what extra EMI precautions do we need to consider for automotive applications?
Automotive applications will have to deal more with thermal management rather than with EMI. So like I said already, if you put a metal shielding around the whole device, you will have no or close to no issues with the sensor. This is the best what you can do. At the end, it comes down to the most cost-efficient solution. And I understand automotive solutions are very price sensitive.
Okay, so thank you very much, Prometheus. We reach now the end of our presentation. We'd like to keep everybody on their busy schedules. I'd like to thank Prometheus again for the presentation, and a big thank you to you all for your joining our event. We hope you found it informative and helpful. For more information, please visit excelitas.com and feel free to visit our Contact Us page to submit any further questions or requirements you have for IR sensing technologies. And also watch out for our post-webinar mail with links to related topics and this webinar's video. I can only say thank you very much and have a nice and good afternoon.